Good afternoon, everyone. Today we present an AI-driven pricing optimization and content enhancement for Airbnb. So Airbnb faces a growing problem, a non-transparent, inconsistent, and often inflated prices. Guests find it similar properties at vastly different rates and creating confusion and eroding trust. The root cause? Pricing is set manually by host and human valuation experts with limited data-driven support. So without a standardized process, hosts miss revenue opportunities, guests lose confidence, and Airbnb risk its brand credibility. So our goal is clear: to implement a data-driven valuation system using AI to deliver fair, market-aligned pricing that removes human bias. So we propose a machine learning-driven pricing model that factors in location and attraction index, room type, guest ratings, etc. And we'll be using Sapphire to follow a full machine learning workflow from data exploration, variable selection, model training, model evaluation, etc. So the outcomes are simple. So we hope the hosts can optimize their revenue and booking rates, and for guests, they have a fair and consistent prices. And for Airbnb, it has improved customer satisfaction and stronger trust. So in short, we turn pricing from guesswork into precision, creating a win-win for host, guests, and Airbnb.
We frame Airbnb's pricing challenge as a supervised regression task that predicts a market consistent nightly price from each listing context, so the output flows straight into the price recommendations. The target is actual nightly price for a 2 people and 2 night booking scenario, and the inputs cover 4 buckets: property attributes such as a bedroom, bathroom, capacity types, and amenities, host quality such as the rating, location indicators such as the distance to the CBD and transit, attraction index, and availability context such as the lead time. Next. The goal is to recommend a price that lifts occupancy with perceiving revenue, and we judge success with ASE and ME on holdout data. We are also watching stability across fold and reality checks against comparable listing. We selected 4 algorithms to balance the accuracy, interpretability, and robustness. First, linear regression with ridge lasso act as a transparent baseline, giving the interpretable coefficient and helping us benchmark improvements. Second, decision trees capture nonlinear split in the data and produce the easy-to-explain rules, making them ideal for the communicating insights to business stakeholders. Third, random forest built an ensemble of the trees to improve stability and accuracy over side trees, reducing overfitting. Lastly, a neural network with one hidden layer let us test a flexible, nonlinear approach beyond the tree-based methods, potentially capturing complex feature interactions. By comparing this diverse model under the same conditions, we ensure that the final choice is driven by both performance materials and business interpretability via ASE and RM.
For now, I will walk you through the work we carry out in preparing the dataset and selecting the most relevant feature for our predictive model. Those steps were essential to ensure that model we built were both accurate and interpretable. We start by examining the raw dataset, which contained over 51,000 listings from the 10 Europe cities. The source file showed that there was no missing value in any predictor or target variables, which means no imputation was necessary. Data exploration also confirmed the validity of the dataset since all prices were greater than 0. Distance were logically consistent with geographic constraints, and capacity value aligned with realistic accommodation sizes. However, several continuous variables had distributional issues. Most notable, price showed extreme right skewness with a skewness of 21.42 and kurtosis over 800. Such extreme skewness will cause instability in regression models, resulting in less reliable predictions. To address those issues, we apply target transformations, the logarithmic function for distance and attraction index to reduce positive skewness, the reciprocal function for mental distance to stabilize variance by managing outliers, And the rest index was adjusted with a square root transformation, while the gas certification overall was squared to correct asymmetry and better differentiate high ratings. For category variable, including bedroom, city, and room type, we used one-hot encoding to preserve their category structure. Binary variables such as superhost status and date type were consolidated into a single indicator to simplify interpretation. Those transformations improve distributional symmetry, reduce the impact of outliers, and prepare the feature for stable, interpretable, and accurate modeling. Once the data was transformed, we performed a feature selection using a combination of exploratory data analysis and source file stepwise selection, aiming to retain predictors with both strong statistically significance and clear business relevance to the target variable price. The process resulted in 16 predictors, recruiting key continuous variable, important categorical features, and city dummy variable that capture geographic pricing differences. However, variables such as superhost status and date type were excluded due to a low predictive power and multi-collinearity as confirmed by the variable importance table. And also, the private room and shared room categories were dropped as they become redundant once room type of entering home or apartment was selected. This dimensionality reduction improved computational efficiency and reduced the risk of fitting, which makes the model more generalizable. With the data clean and the right feature selected, we were ready to move on to model building and testing.
So I'm gonna explain our model training part. So we split our data into 3 parts. 80% of the data is for training, 10% of the data is for validation, and the rest of the 10% of data is for testing. The reason we need to do the data splitting is because those like 80% of data is only for the training, so those data cannot be reused or to the validation or testing parts, so otherwise it cannot predict a really precise prediction. And also we believe that regression models is really a good machine learning models to apply in our class. So we choose 4 regression model. The first one is neural network regression. Second one is random forest. Third one, linear regression. And the last one is decision tree. We also do the hyperparameter tunings. So this aim to get the best model with best setting with the minimal prediction errors. And for the model testing and evaluations part, so we do the different depth and settings for each model, so we can evaluate on the test data set, so we can get which model have the lowest ASE and RMAE, so we know which model with which kind of setting is the best model. For example, like decision trees with 4 depths, we get the 16,000 ASE, but we increase in the setting to 10 depth, the ASE is around 75,000, and we increase it to 20 depth. It didn't improve its performance, so it gonna make the models overfittings, or it gonna make the model training more inefficiency. So the last for the model selection, the decision trees with the lowest ASE is around 58,500 and RMAE with 9.31. Random forest ASE is 15,000 points higher, and RMA is lowest, which is 9.05. So in the end, we choose the decision tree because we believe the lowest ASE is helpful in this case because our data sets outlier characteristics, so it balances the accuracy and simplicity.
So now let me share some key findings from the decision tree model and our recommendations. So our model made one thing crystal clear, is that location sells. The attraction index is the single biggest driver of higher prices. So if your place is near to more attractions, you can charge more, and guests will pay for it. And our recommendation is to make attraction data mandatory and coach hosts to highlight nearby sites in their descriptions. This is a low effort and high impact in revenue. Next, free bedroom wins big. Families and groups love them, and the market pays a premium. So our recommendation is push free bed listings where possible and help hosts to configure space to capture the demand. So we have an interesting finding is that actually small spaces can be gold mines. So for short stays, 1 to 3 guest listings pull in more per night than bigger sizes rooms. So Airbnb should prioritize this in search results and guide the host to on layout tweaks and to match the demand. And the cleanliness scores barely move the needle on the price. So let's stop overweighting them in the pricing models and focus on what truly sells. And finally, city matters. So Amsterdam, Athens, your location alone can swing your price. So our recommendation is to roll out city-specific pricing models for hyper-accurate valuations. So the bottom line is that these aren't just numbers. They are levers Airbnb can pull right now to boost host revenue and gives guests fair value and make pricing transparent and more competitive.
Now that we have addressed the challenges of fair and transparent pricing, we can take the next step, empowering hosts to grow their Airbnb business via Gen AI. We applied Gen AI to improve a Melbourne listing rate 4.92 out of 5. While guest reviews were excellent, the description did not fully use its unique strengths, such as location, self-tracking, and amenities. Our goal was to enhance listing description to increase guest appeal and drive booking intent by highlighting features that align with proven price drivers from machine learning analysis. This include attraction index, suitability for 1 to 3 guests, and location convenience. We use a zero-shot prompt asking ChatGPT to act as Airbnb's professional contextual consultant. It identified missing details, and after refining the prompt, it produced a structured, persuasive narrative plus bullet point highlights. The AI-optimized version was more engaging, clearly highlighted amenities and location benefits, and also increases the clicks, page views, and target inquiries. Finally, we asked for bullet point style highlights. ChatGPT delivered a clear summary showing that attractions, property size, and capacity are top decision-making factors for guests. For why it works, because it directly addresses travelers' priorities, aligned with short-stay behaviors, and use reviews plus market data to create content that resonates. Based on this result, we recommend integrating AI tools for description, updating regularly with review feedback, and requiring attraction data in all listings. That will enhance satisfaction, bookings, competitiveness, and trust. That's all.
Upon the discussion and the application on AI, we would like to address some ethical implications. In terms of data privacy, our AI pricing and description system use the location and data that could rival private attributes. So we protect privacy by collecting only what we need, anonymizing or aggregating fields, categorizing, exact coordinating, honoring consistent and notice, encrypting data in transit and reset, limiting access by role, shortening role log retention, and complying with applicable laws. In terms of bias and fairness, the pricing model replicated historical inequities and undervalued certain areas or host groups. At the same time, Gen AI text might favor majority language or tone and underrepresented minority hosts. We address these risks with fairness-aware training on diverse data, routine bias audits such as MAE party by area or segment, counterfactual checks, and corrective action like the reweighting or calibrated post-processing. For Gen AI, we apply inclusive style rules, block terms, multi-general review, and target sampling for the underrepresentation cases. For transparency, we will use the example explainable AI, showing the feature impact charts and the model cards so hosts understand how pricing is determined and what its limits are. For accountability, we will keep human oversight in the loop, allowing hosts to review or change AI suggestions, backed by regular audits to ensure the system is used responsible. Thank you.